So if you have the restricted three-body problem, so the three-body problem is impossible. If you have the restricted three-body problem, you can have some better understanding of the system. But the simple one, sorry, not restricted, is not solvable. Unless you're trying to go to Princeton or something like that guy. So now we have three masses, N1, N2, and N3. They're interacting, let's assume, gravitational. And again, there's no analytical solution for this problem. And usually you would just do a numerical method. Numerically, you can do this problem. But now let's assume that one of the masses is really tiny. So we have N1 and M2 that are big. Then M3 is M1 and M2 are similar mass. And then you can have, this is a restricted three-body problem, and now you can have some progress in doing the system. So what you would do is that solve for the motion, just like we did for M1 and M2, interacting alone, and then solve for the motion of M3 in the time-dependent potential M1 and 2. All right, questions about what we're going to try to do? So we start with a very, right, so we're going to assume, to make it simple, that N1 and M2 are in a circular orbit. Because they're in a circular orbit, then we can write that there's a angle phi, and it's going to be given by whatever omega is, the angular velocity times time. So, because it's a circular orbit, that means that you have an effective potential, and its derivative with respect to dr is given by 0. So that's looking at that particular point in the circular orbit, right? That's the assumption here. Since we know that this is 3, and we have for the gravitational problem, so at this point we can relate the angular velocity and r. So how do we do that? Well, we have equations such as this one right here, right? This J1 gives us something that relates the time derivative. And therefore, we can rewrite and say that this angular velocity is related to this. And this is the special case of Kepler's law, one of Kepler's law for the spheric circular orbit. All right, so now we have to make another assumption so that we can make the system simpler and easier to solve. We're going to assume that M3 moves in the same plane, as the plane of N1 and N2. All right, so this is a decent assumption. Like for instance, if you look at the moon, Earth, and Sun system, you see that the moon is in the plane of the Sun and Earth, kind of, right? It's not going to be over here, but rather they're all in that. So this is the Sun, this is the Earth. They're around the same. The moon is around here. Like that. So the way that we solve for this, the motion of M3, so we're assuming that we already know from the two-body problems to solve for the motion of N1 and N2. Now we have to solve for M3. And where M3 is in the background of these two bigger systems. So the way that we do this is that we have to change coordinates. So we need a change of coordinates. And we're going to be in a frame that rotates with M1 and M2. Our frame of motion is located at the center of mass of M1, M2. So that's the origin. And it rotates N1 and N2. Does that make sense? So this is a problem I like. I have recently taught numerical methods in physics, graduate level. We solved this problem. So the idea is then that you could set up, there's a, let's say a star here, and then another star here, or a big planet and a big planet. And those two are located right here. And now you're just solving for the motion of this guy. That could be in orbits like this between the two. So all of this sounds complicated, but it's just assume that those two guys are just fixed at two positions. That's what the rotations of the center of mass are. Rotations with the motion of those guys mean that those two are rotating, but your frame is rotating too, so that you don't see that rotation. Okay? So if we want to locate, so for M1, M1 is located R mu over M1 from origin. And similarly, M2 is the same way. All right, so what that means again is that we have a system here. This is the y-axis, this is the x-axis. This is what M2 is. This is what M1 is. Remember, they don't have to be equal in maths. The distance from here to here is R mu over M1. And the distance from here to here is R mu over M2. So in this kind of system, the Lagrangian for M3 in this rotating system becomes 1/2 where this V is just the gravitational potential between them. And we have two distances. Separation 1, 3 is and separation 2, 3 is given by this equation. So for instance, if you have your particle here, M3, that would be where M3 is. Okay, so that's the setup for this problem. It looks complicated because we have the rotation of the mass string. But by putting this guy here, it's a constant and it's rotating there. We actually have a simple system to solve. And it's interacting with this guy and with this guy. We basically erase the interaction between M1 and M2 by accounting for the rotation. All right, any questions? The distance between those two guys don't change, right? But this distances does change. So that's our Lagrangian. We can solve for the equations of motion of the Lagrangian. And I'm going to stop right here because it's almost time for the next test to go.
Why is the M1 M2 instead of M2 M3? The second term of potential.
probably because I made a typo. So this is M1 and 3. This is M2 and 3. Thanks. Yeah, so you see this one goes 1, 3, this one goes 2, 3. All right, so that's where I want to stop.
We will have the gravitational addition for M1 and M2.
Sorry?
With the addition for M1 and M2.
Yeah, that's what we got rid of by going into the rotating frame. Those two guys are actually interacting with each other in this orbit, right? But when we just assume that they're now in a perfect circular orbit, so that we don't have to worry about some of the changes to it. And they're basically rotating, so that's where this interaction comes in. So we make the system a little bit easier and tractable by doing this. And here's the setup for the three-body problem. We have the Lagrangian in terms of the rotating frame. We have the distance between particle 1 and 3 and the distance between particle 2 and 3 in that potential. Any questions before we get started? All right, so the full solution for this problem, for this setup, is actually really complicated. So for instance, 1889, Poincaré discovered chaos using this setup. 1889. He was, well, maybe not chaos as what we know it nowadays, like chaos, but he had this adventure with chaos. Basically, he was working in a dynamical system that exhibit chaos. So therefore, he should get credit for discovering chaos. So very complicated system. It has all of these variants over here. Therefore, it's hard to solve. So to start this, then we have to make a couple of assumptions to make some headway into this problem. So we start by assuming x dot is equal to y dot is equal to 0. So we're going to restrict ourselves to this type of solution. What does this solution mean? What are we doing with that assumption? Sorry? Well, what are we talking about with the x and the y? What is that the position of? So this is the third object, right? Only the third object is not moving. So we're in this rotational frame. So it's not constant the whole thing. These guys are rotating, right? But then the object is stationary. The third object is stationary while everything else rotates around. So that's the first assumption we're going to, this is the solution for this assumption. So the third body is stationary to the other two, and the whole system is rotating. How can that happen? That is not moving. What's happening there? So we have a system there's an object, let's say here, and there's two things pulling on it, yet it's not gonna move. How does that work?
I guess it could be massive, but.
No, it's tiny.
What?
It's tiny.
Yeah, we already assumed that it was tiny.
Yeah.
The forces would be canceling from each other.
Forces canceling out, right? What are the forces? So we have gravitational and we have centripetal or centrifugal?
But which is at the origin, so why would we worry about centrifugal?
So hold on, object does not move with respect to 1 and 2. The whole system is rotating together. And then centrifugal and gravitational forces cancel each other. So this is a rotating frame, right? So therefore we can have the centrifugal force on it. Centripetal is what they make you use in physics 1, right? And they say that centrifugal forces don't exist. Well, they do exist, and that's the one that we're using here. They just want you to be careful there. So what are we solving? Well, we're solving equations like this: mass of object 3, the frequency of rotation, the position x is equal to this dv dx, which is equal to, remember that our potential is up here, right? The one right there. We have the constants 1 and 3, and then we have x plus r mu over m1 r1, 3, 2, plus another term for m2 x minus r mu divided by m2 and the cubic between vectors 2 and 3. So that's for equation for the x. We also have another one for the y, which is equal to this one right here. And we actually have m1 and 3 y 1, 2, cube plus the other term m2 and 3 y cube 2, 3. So those two equations have 5 solutions. Let's look at those solutions. And remember, this term right here is the ones coming out from expanding the 1, 3, and 2, 3 into this things, right? All right. So these two equations have by solutions. Let's look at the first one. Y is equal to 0. So if y is equal to 0, that means that our third object is in this line, right? And remember, y is equal to 0. So we have to solve this equation over here and do some algebra with it. And we have two equations to solve for. So we basically just have this algebraic equation. So this is the equation that we're after. And then when sitting on y is equal to 0, and I can plot here two, let me plot the left side and then the right hand side. When are these two equal? Well, this line right here represents omega squared x, right? And then if we look at that, we'll have portion that looks like this. Now I'm plotting the other side. This. And like that. So this equal, those are the points where that equation is equal. We have here negative r mu over n1. And here we would have r mu over n2. Questions? Yeah. Sorry?
There's a cube.
Yeah, there's a cube right there. So now we have the three positions, 1, 2, 3, that happen to align with this when y is equal to 0. And then the other case would be when y is not equal to 0. And therefore, we take this equation over here too now, right? And so taking this equation right here, from this equation, I get this one. Y is not equal to 0, so therefore I have this term over here, and I can subtract it from this term, and I basically just have to work with this. The M3 and the Y cancel out. And that I can substitute back over here into this other equation. Into that equation. And I'm going to get omega squared is equal to G M1 plus M2 R13 cube is equal to G M1 plus M2 R23 cube. Since you have this and this are equal to each other, that means that R13 is equal to R23 is equal to R. Okay? And those are the other 2 points. Salud. Questions? All right, so that's just doing the algebra, right? So what we have is that there are 3 stationary points. Here, I'm going to have mass 1. Here, I'm going to have mass 2. The first of these points happens to be here, right? So that's actually a point over here. I'll call it L1, L for Lagrange points. Then we have this other point over here. That one corresponds to somewhere around here. This is L2. And then the last one happens over here. So that one might be over here. And then you have the distance R is here, right? Sorry, it's here. So R, and then there's another one just the same down here. Let's assume that they're in the same distance, right? R and R. there's a point right here, L4, and then there's a point right here, L5. So it should look like this guy's L4 and L5, they should look symmetric because they are. It's just that I ran out of paper. So once you have these 3 points, this one and this one are stable, L5, L4. The other 3 are unstable. L1, L2, and L3 are unstable. L4 and L5 are stable as long as M2 is way less than M1. So any use that this could have? Actually, there are some uses. When you look at the Sun-Earth system, the sun is way bigger than the earth, so M1 is way bigger than M2, right? And this exists, this point's right here. And actually there's 2 observatories, solar observatories. And the NASA, the European Space Agency 2, have put satellites in the L1 and L3, in the L2 and L3 positions. For instance, the satellite one is called WMAP and the other one is called Planck. They're used to measure the cosmic microwave background radiation. They're both located in L2 between the Earth and the Sun in this particular line. They have looked at L4 and L5, and it turns out that there's a lot of cosmic dust collecting there. Why? Because it doesn't have to move, right? And it's stable. So it's not good to put satellites there. You get them and they get all dusty. And then there are, when you look at the Sun and Jupiter, these points are important there because that's where the asteroid belt resides. The biggest asteroids are trapped between L4 and L5 when you look at the Sun, Jupiter, and the Sun, Mars system. So those biggest asteroids in the asteroid belt are because that's where they would collect as they orbit with the solar system. Questions? Yeah.
You said so satellites, they put satellites in the L2 position.
Yep.
So it's unstable. So does that mean they have to have some sort of corrective system?
Mm-hmm. Yeah.
So
And it's basically following, like, if it moves this way, it has to keep itself in the right place with rockets.
Yeah.
But it's great for an observatory. Like, for instance, they have a satellite pointed at the sun, right? And it's able to always measure what is happening at the sun and how much space radiation it's emitting and all of that.
Yeah, sensitive that system is it hard to keep it at that unstable point?
Oh, I don't know how hard it is. No, I haven't done research on that. Yeah. But yeah, those points exist and they are being used for those observations. We had somebody, a space physics person I invited for colloquium a couple of years back, and he showed the image from there. And then he said, there is something that passes like this on the image. It looks like a flying object, a UFO. But he said, no, that's one of the planets. And you could see it move in that direction. It looked pretty cool though. So yeah, those don't move from there. And they have little rockets to move them and position them back again. All right, so we're done with the 3-body problem and the 2-body problem and Lagrange. So I'm preparing your homework that you're gonna get.